Welcome, everybody, for our weekly seminar series at the Department of Marine Geosciences. And today we are very honored to host a colleague from not so far away from us, Dr. Alessandro Decarlis from Khalifa University in the United Arab Emirates. So thank you very much for coming. And a little bit about Alessandro. He graduated and obtained a PhD from Pavia University in Italy. During his professional career, he worked as a field geologist for the Italian National Mapping Project at 3 official map sheets, and a researcher involved in basin analysis and tectonics with a strong field approach and a special interest in understanding the sedimentary response to tectonic processes. His research evolved from basin analysis related to various stages of the Wilson cycle in the Alps to the understanding of the tectono-sedimentary architecture related to the underlying crustal structure during variations of the geotectonic setting. He considers up and down scaling from field to seismic observations and the ability to integrate key geological observations into a larger framework as the most important contribution of his research. The field mapping activity in the Italian foreland basin and retroforeland basin drove him to consider the interaction among different successive geothermic environments and to enhance the comprehension of the paleogeographic setting in the Alps Tethys region during Mesozoic and Cenozoic times. Later research in EOST in Strasbourg was related to the study of rifted margin structures, comparing the evolution of the Atlantic and Tethys oceans during field and core data and seismic imaging. He developed research multidisciplinary research, including stratigraphers, structural geologists, paleontologists, petrologists, and seismic interpreters. More particularly, he's involved widely in industry projects that help him to interact, work, and develop new research fields and to get access to data such as high-resolution long-offset seismic sections that commonly are not available in the academic environment. The study of rifted margins was developed with a twofold approach, one directed to the comprehension of sediments and structural elements, and another one more conceptual, oriented to the crust dynamics. Since 2019, he's working at Khalifa University, continuing his research activity in the Alps and integrating it with studies in the Red Sea, Oman, and the Emirates. So again, thank you very much. And today is going to talk about magma or rift basins and talking more about the Alps perspective. So Alessandro, the podium is yours and I shut up. Thank you.
Thank you so much for the presentation. Thank you so much to have invited me here to discuss, to open a little bit of discussion, I hope, with the colleagues and the students at Haifa University. So what about this presentation? What's behind this presentation? Because it speaks about a very large geotectonic environment, and then there is a recall to the Alps. So what is this about? Well, my thought about is that we are living in a very technological era. Most of our students are demanding for high enhanced techniques, technologies, and IT is there, is on board, and AI is coming. Okay, and I just want to make the point of my role as a geologist, and I want to transfer this kind of thought also to your student as well. So, in my opinion, we need to apply all this technology. We need to apply the new incoming techniques or lab analysis and whatever to make models. Okay, but the point, we don't have to forget the field, because from there we came. And this is where we are looking at. That's why I prepared this presentation thinking about assembling our outcome that we have regarding large-scale system in the Alps, in the matter of margin, rifted margin, that is part of my research. I'm a tectonist. Looking at what was the role of the Alps, so how analysis in the field, a field approach in the Alps helps to develop this first-order concept. The first question you may have, some of you may have, is about why we want to use mountain belts, speaking about rifting. Okay. It seems that they are rifting and the mountain belt, they are at the opposite side of the Windsor cycle. You have extension and compression on the other side. So you may think, oh, this is too complex. Okay, you have to analyze a mountain belt, and then you have to read the form. You have to take out metamorphisms probably to start speaking about how a margin is done. Well, this is not actually the story. In fact, if we want to explore a margin, which is a 4D entity, so 3D plus time entity, we need to explore it where we have real data. In real data, we have above water surface. And to explore this kind of data, mountain belts are still the best place in the world. The second answer to this question is, take a look at this map that we have here. There are thousands of maps of the European Alps. It's a very well-known area. So you don't expect so much new thing about these domains. But when you look at this map, you can see homogeneous color in there. What are these about? This is the work of the pioneer geologists that explored the Alps in the last century. They try to group all the stratigraphy that they have in homogeneous groups. So they put similar stratigraphy together. Then when the knowledge about the chain evolved a little bit during the 50s, people started to group stratigraphies into similar stratigraphies into areas which are also characterized by the same structural level. Okay, so this is a tectonostratigraphic approach. They consider an up pile, and they eventually consider homogeneous stratigraphy. They give the name to this domain, which we are not going to, and we remind here it's completely unuseful. Helvetic, Briançonnais is a very complex name. But the point is that these are first-order key observation made on the stratigraphy, and they are, if you look at this picture in here on the right side, they are exactly the terrain which are reminding us the status of the margin. So it means that in the economy, let's say, of the Windsor cycle, the rifting stage will create the first unconformity, stratigraphies, basins, first-order tectonic boundaries that remains throughout the whole evolution of the chain. And this is very important. In the case of the Alps, this is a Jurassic rifting, late Triassic to Jurassic rifting. And then we have a complex passage into an ocean, the Jurassic Tethys that you have heard about. And then the story finished with a collision that was tertiary, mainly Eocenic onwards. What kind of margin we are speaking about? What was characterized by the Jurassic margin? It was a magma pore system. So it's not up to me now to explain you what is the difference between, I mean, I just know that you are aware of this. The point is, one system, the magma-rich system, and the magma pool system are end members, okay? So in one of the systems, you have a lot of magma during rifting. So you don't have to consider the oceanization window, okay? Just during rifting. In the other case, in the magma pool, you don't have magma, or you have a very few evidence for magma. Point is that this is very important for the mechanic extension of the magma, of the margin. So the role of magma is to help, in a way, extending, or not, like in the case of magma poor margin. So in the second case, things can be a little bit more complicated. This is a classical schema that I contribute to develop this started with Gianretto Manachal and co-authors, and I contributed to work out this kind of schemas for the extension of magma pool rifted margin. And in the future, in the next slide, we're going to see what was the contributor of the field to define this kind of a specific schema. If you want, you can call it a model. In reality, this is measureless, okay? So it's more a conceptual schema. We have a stretching. So we are working out a craton in extension without creating real thinning. At the beginning, we only have half graben basins, okay, with the limited amount of thinning. And then we start to develop the real thinning of the crust, okay, in the thinning stage where we create necking zones. Those necking zones are those V-shaped domain which we have the coupling of middle to lower crust tectonics with upper crust tectonics. And in this case, we moved out tectonics to the center of the system in this yellow block, which is called keystone block or H block. The successive evolution of the margin brought to a split of this block, okay? And the onset of very peculiar kind of faults, which are low angle normal fault or detachment fault. So in this dynamics, when you start with this, you see that you pass from a symmetric system on your left side into an asymmetric system. The margin became more asymmetric, recognizing one thick margin on your left side, which is called the upper plate. And on your right side, the lower plate system, characterized by a more horizontal development of stratigraphy, not vertical. So most of the H block remained on the left side in this case. And then the final point of evolution for a rifted margin is the exhumation dynamics. So you see this greenish stuff that came at the surface in the last picture here is not oceanic crust, is subcontinental mantle, okay? So theoretically, at this stage, we are still in a rifted domain, okay? We are not into a passive margin stage. We do not have still created an ocean, a steady state, mid-oceanic ridge. In here, we are dealing only with subcontinental mantle that has been exhumed at the surface. How we create this kind of model, this kind of conceptual template? Well, mixing up the field evidence, that's what we are going to discuss, and some seismic sections, okay, taken from modern margins, in which we have a very limited data. Usually we have geophysical data, and a few of this data are available for our work. Seismic sections are used as a framework to measure the domain we are dealing about, while the outcrops in the field can be used as virtual boreholes. In this case, we gave some attribute, some real solid rock attribute to the seismic section that otherwise are sterile at the first look. So this is material that we published. We made on one side the application for the Atlantic Ocean, in this case, for example, for East India or for the Red Sea more recently. On the other side, we tried to reconstruct the Alpine margin, which was our first interest. So the contribute of the field in this kind of studies can be resumed in this schema here. We have a contribute that regards tectonostratigraphy. So we arranged, we tried to understand where sediments deposited and why, which kind of sediments, especially. We tried to better define the geometry of the rifting system in terms of dimension of each domain, which we find in the field, but also in terms of margin polarity. So we have seen before, and we will see in the next slide, that we are dealing with an upper plate and lower plate system in this asymmetric domain, but how much they are persistent in the field. Okay, if we consider the whole Atlantic Ocean, how much it lasts spatially, this configuration of upper and lower plate. And finally, the field contribute to give us some rocks, real rocks, to speak about the thermal history, okay, of a margin, how the thermal history change and how fluids interact with rocks. So why this is important? You may think that this is important only for oil companies. Okay, I never spoke about oil in my paper. Oil and gas are a part of the game. We are only speaking at this presentation and in general in my research about tectonics, about general concepts. We are not dealing really with the search for oil. Search for oil is a method that companies do better than us, for sure. But you have to think that, and I'm speaking to, especially to the students, gas will remain, is not abandoned, will not be abandoned in the future. And stocking CO2, stocking H2, search for H2. And even, for example, digging out some mineralization like lithium associated to salt are still a matter that regards rifted margin. So the study of rifted margin is not time lost, is where we need to apply, in my opinion, for a future, also a sustainable future. We can start from tectonostratigraphy and see how the field contribute to the general, okay, the general model that we saw before. To speak about this, we need to enter a little bit more in the alpine system. The Alps are not really a simple domain in this case. From this picture here, you can observe that there is a main fault separating two areas of the Alps. In the north, you have a couple of margins, so two conjugate margins that were squeezed together during compression. And to the south, you have an additional margin, okay, which is a little bit isolated, okay, but it makes part of the southern microcontinent that was called, in this case, Adria. And so what we have is that northern area and southern area were coupled along strike of the rifting, okay. So in reality, in the alpine tethys, we have the opportunity to observe more than a couple of margins. There are three margins actually preserved. The first important information that we have is that when we are considering distal margin and proximal margin, we are dealing with a completely different sedimentary architecture, completely different kind of sediments. We can start from the proximal margin, what we have seen before. And at the beginning of rifting, you have only the formation through half graben or graben system. These were studied at the beginning of the story of research in the Alps, in the Southern Alps especially. Here you see a picture. Daniel Bernoulli made his PhD thesis on this in this area, and they are simply beautiful half graben system filled of lower Jurassic carbonate. So most of this material is just carbonate mud or carbonate recycled from a platform that you have on top. For what concerns the depth of this basin, there's a long debate, but it goes from some hundreds meters to 1,000 meters, more or less, or 1,500. We don't know exactly, but this is the range, more or less, which we have to expect. During the evolution of margin, these kind of basin, or let's say their succession, were uplifted, okay, because they became part of this central block, the yellow block in the figure, and this led to a complete erosion of this succession. So in some parts of the Alp, in the central parts of this schema, in the Briançonese domain, we have a sedimentary gap that embraces technically 40 million years, but this is just about the stratigraphy. In reality, the gap, the uplift was a few million years long. But it's very important because allow you to identify the central part of this system. In the most distal part of the rift, the syntectonic sequence are characterized by a completely different behavior. So they start to be clastic. Okay, so the remnants of the previous platform, the previous basin that you formed on top, are destroyed and brought down to a depth that is estimated around 3,000 meters at the beginning of this of the formation of these realms. So it's very important to note that there is a completely different architecture of the sedimentary basins in this case, and completely different kind of sediments. In the Alps, you have areas like breccia nappe, in which you have several kilometers of breccia, ranging from olisterstrom to metric size breccia. And we have kilometers of this, 2, 3, 4 kilometers in some sections. So it's an amazing accumulation of breccia, which has got a counterpart in modern margin. So somewhere you can still spot this kind of classic accumulation. But now in the distal margin, again, we have the maximum complication, okay? For example, in the upper plate, you start to have this mega breccia accumulation, which is very characteristic, okay? But if you go into the lower plate, which is the opposite part, you don't have this huge accumulation, but you have a very, very characteristic feature of the stratigraphy, which is created by the fact that you have exhumation. So low angle detachment systems start to exhume the upper crust, then the lower crust, and then the mantle. And on top, you have this large block, mountain-sized block of stratigraphy, which are possibly transported on top of a sort of conveyor belt, you can imagine, okay? And so in the Alps, in Switzerland, and in the Osterpine domain, you have mountains which are completely allotons on top of the, let's say, of the former detachment system. Here is an amazing picture of these blocks, which remains on top of the basement ongoing exhumation. And all these lines that you have in here were detachment folds, and then were later reactivated during orogenesis as crust. Okay, this kind of information you can only have in the field, where you can explore natural section, where you can explore lithologies, you can measure things. So these are very difficult things to spot, for example, from geophysics. Okay, this is the main approach, the main advantage that we had from the field in deriving a real tectonostratigraphic framework. Thanks to the fact that we can explore also some, let's say, 4D section, because we have ages from dating of the rock, we were also able to understand something more about the dynamic. So we have an extension through the whole margin that we call proximal margin. When we start to thin the crust and generate the distal margin, then we have a complete stop of tectonics in the proximal margin. When we generate the distal margin, the ultra-thin part of the margin, then we have tectonics also so only in there. When we have exhumation, we start to have tectonics in the exhumed part only. So it's like that you concentrate tectonics, you delocalize tectonics into inward domain. Not to mention the change that we have in the fashion, in the architecture of the various basins that you can see here in the lowermost part of the picture. And that was very important because this was verified in the field. So this helped us to define what was the geometry to give measurements to the margin of the Alps at that time, and helped us to assess the correct value, the correct weight, for example, for each domain that we are exploring, the proximal margin, the let's say, distal margin and the exhumed domain. But we also learned that some other complication arose. For example, one of these unexpected complications was the fact that in the Alps, the margin we explored were of two types. We have a conjugate toward the north, and then toward the south, we have a different kind of margin. We have upper plate and lower plate toward the north, and toward the south of this huge line, the periadriatic line, we have an upper plate again. So this was a problem. To find a solution for this, we need to dig out in the literature again and go towards the first idea that Gordon Lister postulated during the 80s. So he explored basinal range, and he found out that these low angle detachment faults were not constantly dipping toward a specific direction. They were flipped. And also Gordon Lister and his co-authors, Davis and many others, they thought that this was observed at the scale of the basinal range locally, but can be exported also at the scale of the whole margin when you have an extensional margin. And that was true. In fact, this was later discovered in the Atlantic Ocean. That is what we have more or less in between Brazil offshore and Eastern Africa and Western Africa, sorry, offshore. So we have a continuous flip of these geometries. And that's what we discovered restarting stratigraphy. So in the Alps, we discovered that there was a main flip of the architecture of this mark. And again, we are speaking about a reinterpretation of a stratigraphy that was considered to be, well, a standard, okay? Was established since 100 here at the time, and was a complete reinterpretation. So the field speaks differently in terms of the age at which and the advance of the knowledge about a specific area. I want to conclude, because I'm running toward the end, this presentation with the last couple of slides in this case that are related to the heating cooling cycles that are one of the main topic we explored lately. And we did this with the specific aim to find out some response to the main problem that we had at that time in the stratigraphy in the field. How our knowledge in the field and our knowledge about the heating cooling cycles in the chain may help us to define some important things about the evolution of margin. This is an example. We explored at one time a basin that was located into the most, let's say, it was a basin just placed on top of an Ekin zone. Okay, so it was floored by detachment fault. And what came out is that we had a depositional age that you can see in it, placed back into arch, and it formed at that stage. And this was proven by fossil content. When we explored the cooling age, tried to determine the cooling age with the uranium thorium annealing technology, we found more or less the same age. How this was possible? We tried different grains, we tried different rocks, and the results were more or less the same. So it was funny, okay? So this would mean that the detachment that was at the base of this basin exhumed the basement so rapidly that the basement was almost instantaneously exhumed, eroded, and redeposited within the basin. And this for us was a sort of shocking idea, because in terms of, let's say, geological time, the necking process was extremely fast. It's like that you stretch the crust for a million years, and then in a very rapid time window, You thin the crust, you generate the uplift of the central block, and you start to open new realms. Okay, and this was possible only thanks to this kind of discoveries. Another quite shocking point, a shocking study for us, a bit we are dealing with the Alps, we are dealing with margins, was this one. We went into the same tectonic position, so on top of one of these, let's say, distal margin fault, and we analyzed the basement. And we found that not only we can spot a rifting-related metamorphism, but we find out that this was really, I mean, more widespread and more consistent than expected. So we find out that rifting can induce a metamorphism on the rocks of the basement. In this case, we analyzed the basement with two techniques. So zircon fission tracks and then uranium tourmaline. And we found out that zircon fission tracks gave us an age, a Jurassic age, while uranium tourmaline gave us Cretaceous age or Eocene age. Means that one was related to the extensional event, and the second one was related to the compressional event, so the alpine cycle. But the cooking during the extensional event was much more than expected. Okay, so we are speaking about more than 300, 350 degrees in this case. And this was unexpected on one side, but extremely important because it means that part of the metamorphism of the Alps is not subduction related or only subduction related, or if you want, burial related, but can also be rifting related. On the other side, this discovery opened new room for eventually some geothermal researches, okay, in modern margins. Okay, so the temperatures are very hot. We thought at one point that we had 90 degrees per kilometer as possible geothermal trend. So to conclude this short overview on the role of the field in investigating margins, we can summarize our work in this slide. So the field gave us the localization of extensional deformation and effects on sediment distribution. This was something that was taken exactly from the study of basins. And this contributed, in a way, to the tectonostratigraphic framework of the Alp itself, but also to the tectonostratigraphic framework of modern margins, if you want. So you know where to pick up things now, for example, to examine an area in which you don't have drilling yet. Then we had this new problem that a few people investigated till now, also in modern margin, that is the large setting of the resistance system. So the geometry of this rifting flips. Okay, so the fact that the margin can change along strike. This has been verified, but is still poorly observed in the field. So the Alps, I think, they remain one of the few places in the world in which this has been observed. And then finally, the heating cooling cycles. So this is an open matter of debate. The analysis on this, especially distal margin rocks, led us to fix some point on the thermal evolution and also on the kind of evolution that we have, so the timing of evolution for the Alps in general, but also for most of the margin we are observing today. And I think that's all. And I hope that this presentation, very rapid, perhaps very condensate, but may help to develop some critical thinking in the students and some questions and whatever. I really hope that someone may have curiosities that we can eventually answer and we can work out.
Thank you very much, Alessandro. It was very enlightening for us. I open the podium for questions from the audience. Are there questions?
Hey, Nicolas, can I ask the question? This is Guy.
Yeah, please go ahead.
Hey, very exciting, very interesting. Thank you very much for your talk. I was wondering, since you have the privilege of actually going out there and touching the rocks and defining those contacts, I was thinking about the analogy proposed by Lister et al. Regarding the flips of polarities between upper plates and lower plates. And when looking at along the strike, seeing these polarities, do you see any kind of inherited reason for these polarities to happen where they are? Like, do they follow any kind of rheological boundaries that were inherited to the rift, or is it too back in time, too old to actually say something meaningful about the locations of these contacts?
No. So, Guy, thanks for your question. It's an open question, actually. I worked in the last couple of years in the inheritance of rifting, okay, in the Alps, okay. I cannot add this to this presentation because it was too much at the end, but we published a paper on the inheritance of the cycle. We have rifting on one side of the Wilson cycle and chain, and it's a long travel, but it's also a short travel on the top. So you can pass from mountain belts to rifting as well. And that's what I'm working actually. So in regards to the flip polarity, it could be that these are previous transfer faults, okay? Me, I'm on this side, I thought, but I cannot demonstrate at the moment. I'm working in the Red Sea in the area of Qusair. We are just trying to demonstrate that the existence of a Paleozoic strike slip system may have pushed through a later evolution of rifting, which is different in the two sides. But at the moment, I cannot demonstrate that this was a real flip. Okay, for sure, these transfer faults exist, and they are located in some specific area, exactly where all the shooter system were, or below some oceanic arches or whatever. So the idea is that is not really the surface configuration, okay, that influence the development of this kind of systems, but is the deep configuration. So lower crust or even the mantle structure that influence this kind of tilting of the system. This is my thought.
Yeah. Thank you very much.
Are there more questions from the audience?
Hi, can I ask?
Yeah, please go ahead.
My name is Alexandra, and I just wanted to clarify back a couple slides where you talked about biotite, and you said that this biotite has metamorphic. Yes, and why not metasomatic origin? Metasomatism?
Metasomatism,
Do
okay.
you, yes,
well,
yes.
We don't know actually. The point is that this area was really on top of a fold. We have circulation of water for sure in there.
Yes, that's why I asked, because usually it's really common.
That may have put some head more. But the point is that if you step back, if you step away from the fold, the whole basement was the same. This kind of biotite is darker, okay? We call it greenish biotite. And we don't know because we never go on this after this paper 2017 we planned to do, but we were unable at one point. We find the same kind of greenish biotite into another place of the Alps where the distal margin was. So it's like a sort of indicator for us. So there was for sure a connection between this biotite and the fact that we have this this kind of heating. You know, this biotite can be also associated to hydrothermal. It's a possibility, but in that specific place, we were unable to find really huge duct for the passage of water. Could be, you know. In fact, the paper was not conclusive. Was just, but the fact is that we have circumflexion tracks that says Jurassic and uranium thorium helium that says later, younger ages. So for us, this was amazing, and we decided to throw the ball and see what happens. But no one searched for alternative interpretation at the moment. It would be challenging to continue this kind of research for who is interested, because in my opinion, is super nice.
Thank you.
Are there more questions?
Nicholas, do you have time for one more question? This is Guy again.
Go ahead. Go ahead, Guy.
Alessandro, I wanted to ask regarding your criteria for defining the different crustal domains. So usually what we do in geophysics is look at crustal thicknesses and the formation styles. And I was wondering how difficult it is for you to reconstruct the rift stage or final rift stage crustal thickness based on the moho you observe at the moment. And how do you cope with that?
No, actually, if you rely only on field data, you can't, because you can't see the moho, okay? And the moho that you have below the Alps is sorry? And the moho that you have below the Alps is still a matter of debate as well. You know, there are some different whatever. So the point is that we are doctors in modern margins, in style action, we use gravity, we use all the possible methods that we have. For this, especially Newfoundland, Iberia are the best conjugate that you can use, and we compare with what we have in the Alps. For sure, what we can observe, for example, is the architecture of the basin, which is something that you see immediately, okay? And this is what I explained. If you want to go a little bit further into the moho problem, then you have to approach the Ivrea Verbano zone. I don't know if you are, if you know the area. This is a part of the Alps that has been tilted 90 degrees, in which you can observe the complete structure from the base of the crust, piece of the mantle, up to the surface. Because during compression, it has been tilted, and you can observe at the surface. And in there, you have a complete section through a thinned crust. And these helped definitely a lot us. You still have this necking zone preserved in the field. So you can really go in there, touch, measure everything you want, observe, and bring to the model that you want to do. I wrote a paper 2023 in Earth Science Review about this, okay, about inheritance. That was a previous question, and about this matter, and it's Decarlis et al. So you can really find it very easily.
I'll definitely look it up. Thank you. Thank you very much.
Keep in touch.
Sure.
Okay, I think that we don't have any more time for questions. So again, thank you very much, Alessandro. We really appreciate your contribution to our seminar. And I hope that you will be coming, not virtually, but physically, to visit us.
Yeah. I have to move to Italy now, but in the future, for sure.
Okay. Thank you very much then. And thank you for everybody.
See you. Thanks.
Bye-bye.
Thank you.
Thank you.